Welcome to AP Biology. Today I want to talk about pedigrees and what patterns you can find from them. So first of all, what is a pedigree? It's just a family tree that shows the relationships through generations of a particular trait. So the trait that you're interested in is going to be the one colored in. So for each trait, tell me if the trait is a dominant trait or a recessive trait. And you could have a codominant or an incomplete dominant trait, but we're not going to be looking at any of those. And then after you talk about whether they're dominant or recessive, decide if they're autosomal or sex-linked. If they're sex-linked, does that mean they're on the X or the Y? Or sometimes you can see mitochondrial or a chloroplast pattern of inheritance. So quick reminder of what an autosome versus a sex chromosome is. So these chromosomes are autosomes. And so the pattern of inheritance that you'll see in autosomes is that you can get the trait from either mom or dad. Mom and dad can give them to either sex baby equally. Sex-linked traits are either X-linked or Y-linked, more commonly X-linked because it's a bigger chromosome, and these are the sex chromosomes. So remember, girls in mammals and fruit flies are XX and boys are XY, and so if you're a boy, you get your Y chromosome from your dad and your X chromosome from your mom, and you give your Y chromosome to your boy children and you give your X chromosome to your girl children. Moms give either X to either kid. So let's take a look at some pedigrees. So take a look at this one and maybe pause the video and tell me if you think it's dominant or recessive. And then once you decide that, is it sex-linked or is it autosomal? So what you want to look at is if it's in every single generation, as in here's somebody who has the trait. We're always looking at the colored in ones, the black one here. So this boy has it. I probably should have mentioned that the squares are males, like SpongeBob SquarePants, and the circles are females. They will tell you that in the problem, but it's probably good to just know that so you don't have to try to keep track of a million things. So here's a boy who has it, and he got it from his mom, who got it from her dad. And here's a boy who has it, same thing. I can trace it up the generations. It never skips, as in, here's a girl who has it, both of her parents have it, that dad got it from this one, and so on. So for every single person who has the trait, they also have a parent with a trait. So I am guessing that this is a dominant trait. Now, it might not be. It could be that it's just a fairly common recessive trait, but it does not skip generations. So let's take a look. I want to draw your attention to this part over here because sometimes it's just a best guess and sometimes it's a, oh yeah, for sure. So let's say it were a recessive trait. Little r, little r, little r, little r. If you do the Punnett square between these two parents, all the kids should be the same, and they're not. So therefore, it is not recessive. Therefore, it has to be dominant. So that was wrong. So if you're not sure, draw out some letters and see what what you think it is. So let's say it's dominant. Let's say big D is for the dominant trait. These two parents could be heterozygous and they could have a kid who's different. So I'm going to say, yeah, this trait is dominant and the proof is in this family right here. So now, is it autosomal or is it sex-linked? So if it's sex-linked, you would have, let's see, we know it's dominant, right? So X and Y. So it wouldn't be on a Y chromosome because girls can get it. So it would have to be on an X chromosome. So let's say the trait, the big D, is on this one. That means he would give it to his daughter, right? Because his daughter should get the X chromosome, and he would never give it to his son. And here I have a son with it, so it can't be that. And you might be thinking, okay, here's the boy, and maybe he got the big D from his mom, right? Because he got the Y from his dad. So maybe that X with the big D came from his mom. Well, if it did, and this were dominant, then mom would be colored in here, and she's not. So thus and therefore, this is an autosomal trait. So that means if you wanted to write the genotypes of everybody, let's see, we've got big D here. This one's recessive, little d, little d. I could go in and draw in the little d's for everybody, right? Yada, 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 yada. Okay. I know everybody who's colored in has at least one big D. So I'm going to do this. And I know they have another one, but I'm not there yet. Okay, so I know this kid right here has a parent who's recessive, so that means they're like that, little big D, little d, right? They have to be heterozygous. These I know are little d because the big D is the dominant and they would have to be colored in. This is big D, little d because they had to get their little d from the dad. Let's see, this one's little d, therefore I know that these are heterozygous. And these kids, actually, I don't know. Because if you do a Punnett square between heterozygous folks, you could get babies who are homozygous or heterozygous, right? You could get this baby or this baby. And so I don't really know what these are. So I'm just going to write a question mark. They're big D something. Yeah. And notice how it doesn't skip a generation, meaning everyone who has it has a parent who has it, right? But notice that it's lost here. That's okay. You can still have a dominant trait that someone just, doesn't happen to get. So autosomal dominant for that one. So what do you see in autosomal dominant pedigrees? It's usually pretty common in the pedigree. It's found in every generation. So I can see here that it's lost. That's okay. I'm not worried about it. Everyone who has it has a parent who has it. You can trace it right through the generations. That's what I'm looking for. It's okay if it's lost somewhere. Sometimes kids ask, what is the triangle? Well, that's if they forgot, if nobody kept good records and they didn't write down whether the babies were boys or girls. All right. Here's another one. What type of pedigree is this and what's your proof? Okay, so what I want you to notice here is that here's someone who has it and the parents do not have it. That means it's got to be a recessive trait, right? Because if it were a dominant trait, that dominant trait would come from a parent, right? We're assuming no spontaneous mutations in this. We're just assuming all of the traits came right from the parents, okay? So here's someone who has it. They had to have a parent who also had that gene, right? That allele. Where else would they have gotten it from? So therefore, it's got to be a recessive trait. So this one, big R, big R, little r. So the big R, I will say, is like the not trait. And the little r is the trait that we're looking for. So this trait is recessive. You might be wondering what the double line is. So who is this person compared to this person? So besides the fact that they had 3 children together, they also have grandparents, which means that they are cousins. So most societies have rules about not marrying your first cousin, and the reason being, like, your kids might be just fine, but if you have some recessive trait that's bad, you are more likely to have a cousin who also has that recessive trait and have kids with that recessive trait that are homozygous. If you married someone who is not related to you, you're more likely to just not have that same bad recessive trait in that random stranger. I mean, they could, but it's a little bit less likely. All right, this is probably not some horrible trait, though, because you can see with these, this family, all the kids have it, and these folks grew up and had babies, so it must not be a lethal or deadly trait. So anyway, it is autosomal also. So how do we know that? Well, here's a girl who has it and here's a boy who has it. If it were on an X chromosome, let's do a different color here. Let's say this were on an X chromosome. Here's a girl. We said it's recessive. It would have to look like this, which means she would have gotten one X chromosome from mom. Well, that's fine because mom could be heterozygous. Her other X chromosome had to come from dad because he only, right? He gives her one of the X's and he only has one X, so the other's a Y. He would have to be colored in if this were on an X chromosome. Can't be on a Y because the girls have it. So this one has to be autosomal because this is not the pattern of inheritance. The dad would have to be colored in and he's not. All right. What is this pedigree and why do you think so? Okay, so first of all, you see it in every generation. I mean, I know it's like lost right here, no problem. What I mean is that everyone who has it also has a parent who has it. You can trace it right up through the generations. So this person has it, so does their dad, and so does that one's mom, and so does that one's dad. Every single person who has it has a parent who also has it. You can trace it right up exactly, um, exactly through the generations. We're usually looking at a dominant trait when that happens. Okay, so now the next thing I want you to look at. So first of all, we said dominant. Now, this is a tricky one. Notice here's a dad. Notice that he gives it to every single one of his daughters. This is not his daughter right here. This is his daughter-in-law. So here's the guy, right? And here's his son. And this is just his son's wife or his son's maid. So this is not his daughter. It's his daughter-in-law, right? So anyway, here's a guy. He gives it to every daughter, but not any sons. Here's a guy. He gives it to every daughter, but not any sons. Here's a guy. He gives it to every daughter, but not any sons. What is it that a guy gives to every daughter, but never a son? His X chromosome. So this is X linked, or more generally, you can say it's sex linked. Sex linked means it's either X or Y linked, but in this case, more specifically, it's X linked. Don't confuse that with linked genes, which are two different alleles of two different genes on the same chromosome. This is just a gene that happens to be on an X chromosome. Okay, so you might be saying, hold on, wait. This doesn't make any sense because here's a mom and she gives it to one of her sons but not the other, and one of her daughters but not the other. Yeah, that's fine because mom has two X chromosomes, right? So she can be heterozygous, and this X chromosome with the big D can go to either a son or a daughter, right? And maybe the other one, X with a little d, went to that son, and the X with a little d went to that daughter. And then they all were able to get, maybe here's dad, X with a little dy. Remember, it's the big D that gives you the trait here. And so she got the little d from dad. She got the little d from dad. He got the Y from dad and the Y from dad, right? So mom can pass it on to boys or girls because she has two X chromosomes. It's the dad's pattern of inheritance that's interesting. And then also notice that dad is always getting the trait. A man, sorry, is always getting the trait from his mom. Let's see, boy here gets the trait from his mom. Boy here gets the trait from his mom. So who does dad give the trait to, and who do the boys get the traits from? So that one is X-linked dominant. So notice that the fathers pass the traits on to all of their daughters, but never their sons. And notice that mothers can pass it on to either daughters or sons. Okay, here's another one. Now, the thing with this one is they were very, very kind because they told you that a half colored in one means a carrier for the trait. So a carrier is someone who's heterozygous but doesn't actually have the disease or the disorder or the trait, but does carry it, which means it's got to be recessive. So you know right off the bat this is a recessive trait. So second thing to look at. So in other words, they might not have shown you these at all. They might have just colored the ones in that are colored in and not colored in these at all. And you'd notice that it's skipping, that someone has it and the parent doesn't. So that means it's recessive. Okay, so notice here that every single carrier is a girl. Every carrier is a girl. Wow. What is it that only girls can carry? X-linked traits. Notice that generally the boys are the ones who have it. The boys have it way more often than the girls. Here is a girl who has it. So if it's on an X chromosome and it's recessive, there she is. That means her mom has to be a carrier and her dad has to have the trait, right? Or her mom could actually have, she could be little r as well, but she has to at least be a carrier. All right. Yeah, does that make sense? So X-linked recessive traits include things like hemophilia or color blindness. I've had a couple colorblind boys a year generally for most of my career. I've only had one girl with color blindness. X-linked recessive traits are much more common in boys because boys only need to have one of the X chromosomes with the traits on it, and they have the trait, right? So this boy's colorblind. This girl, even though she carries the allele, she's not colorblind or whatever the trait is because she has a normal one as well. So girls can be carriers, boys cannot for X-linked recessive traits. Now, if you go backwards here to our last recessive one, this one, um, boys can definitely be carriers for autosomal, right? This one is an autosomal, meaning it's on any of the other chromosomes, right? Autosomal means all of these. So do boys have autosomal traits? Well, yeah, they've got 22 pairs of autosomes, so they can definitely be autosomal. But notice that boys can be carriers for this, just as easily as girls can be, right? But for sex-linked stuff, for sex-linked traits, boys cannot be carriers because they only have one X chromosome. Okay, sometimes the carrier is shown as a dot instead like this. And again, this is going to be a sex-linked recessive because girls are carriers and boys have the traits. If you have a carrier, it's got to be recessive, right? If girls are the only ones who are carriers and mainly boys have the traits, then it's X-linked recessive. Okay, sometimes the carrier is not shown. And so here you have someone who has it and it's skipping a generation, right? Here you have it, but the parents don't have it. That means it has to be recessive. In this case, it's very likely X-linked, but it's kind of a small pedigree, so it's hard to tell for sure. Definitely not Y-linked, right? Because the boys would all pass it on to their sons. But as you can see here, here's a boy who has it. The daughter here must be a carrier because her son has it. And then another generation, the girl's a carrier, a boy has it. So this is probably X-linked recessive. Definitely recessive. Looks X-linked to me. Kind of a small pedigree though. Okay, this is a tricky one. Notice here, it's in every generation. Notice that a guy gives it to his son. Here's a guy, he gives it to both of his sons, all of his sons. Here's a guy, he gives it to all of his sons. This is not his son, right? That's his daughter's husband. So that would be a son-in-law. Here's a guy, he gives it to every single one of his sons, but not his daughter. Here's a guy, he gives it to every son, well, one son and no daughters. It's only present in boys, and girls are not even carriers for it. So, what is it that dad gives to every son and never a daughter? Those would be Y-linked traits. I am not going to, or sex-linked more generally if you want. I would absolutely not say dominant or recessive because boys have one Y chromosome. You would have to find a boy who's XYY to say whether it's dominant or not, and they are not going to do that to you. So just Y-linked is all you need to say for this one. Okay, this is a really hard one, and you do need to know this one though. This is kind of tricky. Okay, so notice that it's in every generation, right? I know it's lost here, but like everyone who has it has a parent who has it all the way up. Okay, here's mom. She gives it to every single child, whether it's a boy or a girl. Notice this is an in-law, right? A son-in-law. This is a daughter-in-law, right? This is a son-in-law. Okay, here's a mom, gives it to every single kid. Here's a mom, gives it to every single kid, right? These are not her kids, those are her kids' spouses. Here's a mom, gives it to every single kid. Here's a dad, doesn't give it to any kid. Here's a dad, doesn't give it to every kid. So what is it that a mom gives to every single kid and a dad never gives to a kid? That is a mitochondrial trait. Or if you're a plant, could be a chloroplast trait or an amyloplast or a chromoplast, any plastid. So if this is people, it's a mitochondrial trait. If it's a plant, it could be either mitochondrial or chloroplast. So that's because eggs are really big. You've got 23 chromosomes in the nucleus of your egg, and sperm are very small. There are also 23 chromosomes in the sperm. So there are some mitochondria on the midpiece of the sperm, but they don't generally make it into the egg. So pretty much the zygote is going to come from the two of these together, right? I don't know, this plus this equals zygote, right? So the zygote has wow, I didn't mean to draw that small, but it's got the 46 chromosomes. You get half of those from your mom, get half of them from your dad, but your mitochondria you get from your mom. Okay, I might be drawing them a little too big. All these mitochondria, you got these from your mom because the egg is really big and has the mitochondria and the nutrients and all the other organelles in it. Whereas the sperm are tiny and they don't really, they're just, the whole purpose of the sperm is to bring the 23 chromosomes from dad to the egg. And so even though there might be some mitochondria on, there are some mitochondria on the mid piece there, they generally do not make it into the egg. So you get your mitochondria from your mom. And that is my story.